Solar and wind power evoke a wide range of emotions. Some are highly optimistic, while others are extremely pessimistic. In this episode, I will discuss key facts about solar and wind power. I'll discuss the good, the bad, and the ugly aspects. But first, a very brief introduction to solar and wind power. In case of solar power, semiconductor materials such as silicon are used to convert sunlight to electricity. In case of wind power, wind turbines are used to convert the energy in the wind to electricity. These technologies are very different from fossil fuel technologies such as natural gas power and coal power. In case of fossil fuel technologies, natural gas or coal is burned to produce heat energy, which is then converted to electricity. The contribution of solar and wind power to global electricity was trivial until a couple of decades ago, but it has increased very rapidly in recent years. The share of solar and wind power is close to 15% currently. With that, let us move on to the review of the good, that is the positives of solar and wind power. The first positive is that the sunlight and wind sources are super massive. The sunlight or solar energy received by Earth in just 1.5 hours is comparable to the energy consumed by the global population in a year. What about wind? There's enough wind energy to supply over 5 times our yearly global energy consumption. So in theory, the potential for solar and wind power is extremely high. The second positive is that the life cycle greenhouse gas emissions from solar and wind power are very low. Obviously, this is a critical advantage from the viewpoint of addressing our climate challenge. The costs of solar and wind power have decreased markedly in recent times. This leads to the third positive. Solar and wind power currently have a low levelized cost of electricity or low LCOE. This metric is often used to compare the costs of different technologies in the power sector. LCOE includes the upfront cost and operating and maintenance costs of the power technology over its lifetime. I must make an important note here. The LCOE costs of solar and wind power do not provide the complete picture. We must be very careful when comparing costs of solar and wind power with other technologies. I'll discuss more about this later in the episode. The fourth positive is that solar and wind power do not emit pollutants during operations. This is expected, since they do not burn fuel to produce electricity. Solar and wind power are attractive solutions for addressing climate change because of these major positives. However, these technologies also have some key drawbacks. We will discuss these drawbacks or the bad of solar and wind power next. I will spend more time discussing the drawbacks, but this is only because the drawbacks are far more complex to discuss. The drawbacks of solar and wind power stem from two key facts about their sources. 1. Sunlight and wind are very dilute sources of energy. And 2. They are intermittent sources. That is, sunlight and wind are not available as and when needed. Let us first consider the drawbacks associated with the dilute nature of solar and wind energy. Metrics such as energy density and power density provide information about the dilute nature of the energy sources. Based on any reasonable metric, solar and wind energy are more than 1,000 times dilute compared to fossil fuels. We'll review the case of solar power as an example. Earth receives massive amounts of sunlight, but the amount of sunlight received per unit area is small. So it is challenging to capture the sunlight. Why? Because it is difficult to harness energy from an extremely dilute energy source. For example, it is very difficult to fish in a large lake that only has a few fish. The dilute nature of the energy sources leads to two drawbacks for solar and wind power. I'll discuss these next. Solar and wind power do not burn fuel to produce electricity, but they require far more materials compared to fossil fuel technologies. Their large need for critical minerals is especially important. Critical minerals are those that are required for important applications and have a risk of supply disruption. Example applications are high technology devices, defense applications, and energy technologies. Solar power requires 16 times more critical minerals compared to fossil fuel power per unit of electricity produced over the life of the power plant. Onshore wind power requires 12 times more critical minerals, while offshore wind requires 14 times more. This is not a problem right now, but the large need for critical minerals can become a serious challenge when the use of solar and wind power is increased massively. I'll discuss more about this in a later episode. The land requirements are also much higher for solar and wind power. A utility scale solar power plant requires over 100 times more land than natural gas power plant to produce the same amount of electricity per year. A utility scale wind power plant requires several hundred times more land than a natural gas power plant. The power plants are usually built near high population centers to improve economics and minimize electricity losses. Land access can be an issue near highly populated regions. This will especially be the case when the use of solar and wind power is massively expanded. Alternative options are available to eliminate the land challenge. Rooftop solar and offshore wind do not require any land, but rooftop solar and offshore wind are far more costly. For example, in the United States, rooftop solar is over 2 times more costly per unit of electricity produced compared to utility scale solar, and offshore wind is 2.5 times more costly than onshore wind. Earlier in the episode, I had mentioned that we must be very careful when discussing costs of solar and wind power. Next, we'll review why that is so. The intermittent nature of sunlight and wind leads to a major difference between how electricity is supplied by the different power technologies. Fossil fuel and nuclear power can supply electricity when we need it. The supply from these technologies does not depend on weather conditions. On the other hand, solar power can supply electricity only when there is sunlight. Wind power can do so only when the wind is blowing. Why is the nature of electricity supply so important? Because our society has stringent electricity needs. We need continuous electricity for certain applications at our homes, industries, and other facilities. For other applications, we need electricity in short bursts. The demand for electricity fluctuates with time. Our current lifestyle is possible because the electrical grid can supply electricity to meet our 24/7 demand. Operators control the supply of electricity such that it matches the demand every second, every minute, and every hour and day of the year. Solar and wind power are not well suited for this. Why? Because operators cannot control the output from solar and wind power. Weather controls their output. There is uncertainty associated with solar and wind power. Also, the electricity output can vary dramatically. This is because the amount of sunlight and wind can vary hour to hour, day to day, and season to season. This has important implications. Solar and wind power produce high amounts of electricity during certain times. For example, when the sunshine and wind are at their peak. But certain other times, when there is low sunlight and wind, they produce very little electricity. Moreover, the low sunlight and wind conditions can extend from many hours to weeks. Think about the cloudy and calm days we experience from time to time. This means that solar and wind power cannot be used to meet 24/7 electricity demand without the use of supporting technology options. A high share of solar and wind power in the electricity mix requires the extensive use of supporting options such as long duration energy storage, backup generators, and massive electrical grid upgrades and expansions. These options are not cheap and add substantially to the electricity costs. For example, the long duration energy storage is very expensive currently. The costs of these supporting options must be included when discussing high share of solar and wind power. The LCOE metric that we discussed earlier does not include such costs. Efforts are underway to decrease the overall costs associated with solar and wind power. I'll discuss the future costs of electricity in a net zero world in the next episode. The use of the expensive supporting options is not required at low to moderate shares of solar and wind power. Currently, many regional grid systems have a 10% or higher share of electricity from solar and wind power. We'll review how these systems adapt to the deficiencies of solar and wind next. Each grid system has some level of flexibility, that is the ability to do more than which is typically required. For example, every system needs to have some excess electricity generation capacity. This is critical for when some power plants are unable to generate electricity because of operating or other issues. Such flexibility is needed to maintain a high reliability of the system during periods of stress. A grid system can adapt to the deficiencies of solar and wind power by using the available flexibility. Several adjustments are needed during the periods when the output from solar and wind is too high or too low. One example is import or export electricity to and from neighboring regions. Another example is to curtail or decrease output from solar and wind power during peak periods. A third example is to increase or decrease the output from existing dispatchable power plants. Most of the adjustments cause a suboptimization of the system, that is, they have a negative overall impact. This is expected considering that these adjustments are made to adapt to the deficiencies of solar and wind power. The need for the suboptimal adjustments increases as the share of solar and wind power increases. I'll discuss California as an example. The share of solar and wind power has increased rapidly in California, from about 3% in 2010 to 27% in 2022. The need to curtail electricity has also increased rapidly. The amount of electricity curtailed from solar and wind power has increased from a trivial amount in 2010 to over 2.5 billion kilowatt hours in 2022. How much is this curtailed amount? It is a small percent of the solar and wind power produced in California, but the total amount is not insignificant. Over 60 countries in the world use less electricity than this per year. The African nation Chad, which has a population of 18 million, uses only a tenth of the electricity curtailed by California. Solutions to decrease the curtailment are available, and California will use this in the coming years. But the solutions are not cheap. They will add to the overall cost. The costs associated with the adjustments that are required to adapt to the deficiencies of solar and wind power are not included in the LCOE metric. This means that the LCOE metric only provides partial costs for solar and wind power. The US Energy Information Administration (EIA) lists solar and wind power in a separate category to prevent direct LCOE comparisons between the different power technologies. Solar and wind power are listed as resource-constrained technologies, while fossil fuel and nuclear power are listed as dispatchable technologies. Next, I'll discuss the ugly aspect about this topic. Currently, we are amidst an ugly debate about solar and wind power that is filled with misinformation. Proponents of solar and wind power only focus on the positives. They ignore or downplay the drawbacks and the related implications. On the other end, detractors only emphasize the drawbacks of solar and wind power. The misinformation from both extremes is leading to a major confusion about the path forward. For example, some people now believe that solar and wind power are perfect solutions to address climate change and that no other solutions must be considered. Others believe that solar and wind power cannot provide reliable electricity and should not be used. Such ugly distortions of the facts are making it more difficult to address climate change effectively. I'll wrap this episode with a quick recap. Solar and wind power have several important advantages. They are powered by almost limitless sources. They produce low greenhouse gas emissions and have a low LCOE. They do not use fuel and so do not emit pollutants during electricity production. The drawback for solar and wind power stems from the dilute and intermittent nature of sunlight and wind. Solar and wind power require far more land and critical minerals than fossil fuel technologies. They produce high levels of electricity during certain periods and low levels during some periods. Because of the variable and uncertain nature of the output, solar and wind power can provide low-cost electricity only when their share in the electricity mix is low to moderate. Even so, the true cost is more than that provided by the popular LCOE metric. This is because the LCOE metric does not include the costs arising from the suboptimal adjustments that are essential. The suboptimal adjustments are required to adapt to the deficiencies of solar and wind power. At high shares of solar and wind power, it is essential to include expensive supporting options such as long-duration energy storage, backup power, and massive grid upgrades and expansions. Ugly distortions of facts are making it difficult to use solar and wind power efficiently to address climate change. Overall, the facts show that solar and wind power are important technologies to address climate change. But it is also important to consider their drawbacks when developing energy policies to address climate change. We'll discuss more in a future episode.